Hi, everybody. Dr. White here with a little wrap-up section in the textbook called Strategies for Integration, where they really try to bring together all of the techniques that you've learned and encourage you to look at new problems where you don't know in advance what technique is going to be useful. The idea here is to develop your abilities, your dispositions for creativity and for persistence. There is no surefire way to find the antiderivative for a function. Some functions don't have a closed form antiderivative, meaning that there's no combination of arithmetic and trig functions and logs and exponentials and raising to powers, familiar things that could be used to make a formula for a function that's the antiderivative. Sometimes you just can't find one. And even when there is one, there's no one single recipe that will always find that antiderivative that you could just apply that recipe without even thinking. That just is not the case. So you're going to have to be prepared to, kind of try something, see that it doesn't work, try something again, learn how to be creative and persistent in your thinking. The book does offer some suggestions to kind of get you started, and I'll go over some of these suggestions to show their power. So one suggestion is simplification. Say you got this antiderivative you got to find. Okay, that's a tough one to find an antiderivative for because it's a product of two functions. And there's no easy rule that says like product of integral of a product is product of integrals. There is no such rule. But if you just use algebra simplification, just square out the x plus 3, and then distribute through, FOIL out this product here, and then gather like terms. This is much easier to deal with. We can find the antiderivative with product rule, x to the fourth over 4, x cubed over 3, so on, and the constants hanging around outside with the constant multiple rule. So this is going to be much easier to deal with. Algebra simplification can turn a difficult integrand into a much easier integrand. So another example, here's a fairly tough integrand, but let's just try to simplify it down a bit so that either the numerator or the denominator is more simple. Well, one way we could try this is with some long division. Let's take the numerator, I'm going to write it as x squared plus 1, and we're going to divide by the denominator, 1 minus x squared. And I think, well, how many times does 1 minus x squared go into x squared plus 1? Well, it goes in minus 1 times. If I multiply 1 minus x squared by minus 1, I will get a plus x squared and a minus 1. And when I subtract off, the x squareds cancel. Plus 1 minus a minus 1 is a 2. There's my remainder. And so this fraction is the quotient of minus 1 plus the remainder over the denominator. So that's a little simpler. And then we look at this difficult fraction and we try to make the denominator simpler by factoring it. And then we realize, hey, this is going to be a lot easier. This piece here, the antiderivative is easy to find, minus x. This piece here is ripe for the partial fractions technique with distinct linear factors, so that's great. Another suggestion they have is just to keep in mind the possibility of doing U substitution, even when it's not immediately obvious. So here's a tough integrand. And this one, you have to have some foresight. You have to have some derivative rules firmly in mind in order to recognize what to do. So I'm just going to advance over here. The derivative of tangent inverse of u would be 1 over 1 plus u squared. And if you have that firmly in mind, then when you see something like this, your eye might be drawn to this. And you say, well, I see the 1 part and the plus part, but where's the square part? Well, what if I were to write x to the 8th as x to the 4th squared? Then I would be looking at a 1 plus something squared, kind of similar to this inverse tangent derivative rule, okay? And then looking up at the top, 5x cubed is kind of like the derivative of x to the 4th. Maybe u substitution will work. So let's let u be x to the 4th. Du is 4x cubed dx. Dx is du over 4x cubed. Plug in what you can. The x's will cancel, and sure enough, you're left with something that you can finish. Okay? So think about using u substitution even if the choice for u is not immediately obvious. The better you know your derivative rules, the better chance you have of finding a good u substitution. Integration by parts, of course, a technique we learned. So although there is no easy rule for the integral of a product, when there is a product, and particularly when the two parts of the product aren't both like polynomials, like in our first example up here, you know, when they're kind of different little things, like here, then maybe integration by parts is a good idea. But again, you want to apply your foresight to decide what to do. You need to make sure that the integral of the v du is going to be something that's easy to get. And if you're thinking ahead, you can say, you know, the derivative of log x is going to be a 1 over x, and that might help cancel out polynomials in x. So let's make the choice for u to be log x. Dv has to be everything else. V would be x to the 4th over 4. Du is 1 over x dx. The uv comes down to this, and the minus, and the minus the integral of the v du leaves us with something where there's some cancellation in the x's. And the resulting antiderivative is very easy to deal with. Trig integrals, another thing to think about. Think about them especially if you're looking at powers of trig functions, you know, like this one here. The thought is, could I somehow mix in a power of one trig function with just power 1 of the other trig function? So, like, could I mix in powers of sine with just one cosine, or powers of cosine with just one sine? Let's try to mix in powers of sine with just one cosine. So if I want just one cosine, I'd better split off one cosine, and I'm left with a cosine squared, but that's 1 minus sine squared. Multiplying all of this through, I'll have a sine cubed times the cosine of x, and I'll also have a sine cubed times the sine squared times the cosine x, so that's a sine to the 5th cosine x. And now it's easy where you let u be, that should be a sine of x, not a cosine of x. So I will make that correction in the notes that you see. There we go. Trig substitution. So trig substitution is useful when you see a squared minus x squared minus a squareds, x squareds plus a squareds, particularly if they're square rooted, can be very useful. So, you know, just be on the watch out for those appearances, and then see when it's okay to use it. Now, both of these examples, it's okay to use trig substitution, this one here and this one here. But make sure you don't overuse trig substitution. In this first example, you don't need trig substitution. A regular u substitution is going to be fine. Let u be 1 plus x squared, and du will be 2x dx, which is just a constant away from what you got left up here. Okay, and you'll end up with a integral of u to the negative 1/2 problem, which is going to be easy to do. Save your trig substitution for stuff where regular u substitution appears not to work, like this one here. And then, with the 1 plus x squared, the recommendation is x is the 1 times tangent of theta. Dx would be secant squared theta d theta, and on you go. The partial fractions technique, so you know that you're going to be looking for that, particularly when the denominator and the numerator are both polynomials, and look at that denominator, factor it as much as you can, and then off you go. Now, there's another strategy that's not listed in the book as a strategy, but I think of it as like a meta strategy, and that is combine strategies that we've suggested so far. That's kind of the creative thinking. So say you're looking at getting an antiderivative of that function, which is mighty difficult. And so you might try things. You might say, well, could I do regular u substitution with u equal e to the 4x minus 1? And you can either scribble down or you can think ahead. What's the derivative of u? It would be e to the 4x times a 4. Derivative of the 1 is 0. And what's left here is not e to the 4x, it's e to the 2x. It's not a constant multiple, of the derivative of u. So probably that u substitution would not work. You can try e to the 4x and you get the same problem. The du would be 4 e to the 4x dx, and that's just not a constant multiple of e to the 2x. You could try maybe integration by parts. So let the u be this, and then the dv would have to be everything else. And finding the v won't be too bad. That would be e to the 2x divided by 2. The du, though, would be 1/2 e to the 4x minus 1 to the negative 1/2. So there's a square root in the bottom. And then there's going to be an e to the 2x. There's going to be e to the 4x times a 4 on the top because of the chain rule, which will not, quite cancel out with the v when you try the integral of v du. And so that probably is, it might not lead to good places, At any rate, we can't see ahead that we're definitely getting to an easier problem. But why not try this? If you've got your properties of exponents firmly in mind, and if you're looking for opportunities, then one thing you might be wishing is, gee, I wish that this could look more like one of these trig substitution things, like this. I wish that this were like this. What would I have to do to make it like? Well, the a would need to be a 1. 1 squared is 1. I do have that. But I need to have something squared, in that first spot. Do I have something squared in this first spot? Well, I do, actually, because e to the 4x is e to the 2x squared. So make that algebra simplification. And then a u substitution suggests itself to you. Let u be e to the 2x. Du would be 2 e to the 2x dx. And e to the 2x dx is just half of that du. And so when you do your substitutions, you get to something that can be handled with trig substitution. Let u be the secant of theta. And on we go. So that's an example of combining strategies, an algebra simplification, a u substitution, and then a trig substitution. But the key is that you're thinking ahead to the possibility of the trig substitution. And the only way to be thinking ahead like that is to know your properties of exponents well enough that you can recognize that e to the 4x as e to the 2x squared. The book lists 3 other strategies. I call them backup strategies. So like if all of your attempts fail to find an antiderivative using these kind of computational methods that we've been learning in chapter 7, then there's still options. You could try to do some algebra simplification, or to make your integral look like the form of one of the integrals in the integral tables at the back of the book, and you can apply those. If that fails, if you can't find something in the integral tables, then maybe you could go to a computer algebra system like Wolfram Alpha and ask for the antiderivative and see if Wolfram Alpha can do it. Now, this often meets with success, but sometimes Wolfram Alpha, even when it thinks it succeeds, it delivers the integral, the antiderivative in a form that might not be useful for you to work with. And another possibility, if your antiderivative appears as part of like a definite integral problem, so like, gee, I wish I could get this definite integral with the fundamental theorem of calculus, but I'd need the antiderivative of e to the negative x squared. Well, turns out there's no closed form antiderivative for f of x equal e to the negative x squared. You could try all day and night, and you could ask for the antiderivative of e to the negative x squared in Wolfram Alpha, and it would kind of spit out that it can't do it. But don't worry, there are ways to numerically approximate definite integrals that we'll learn about in section 7.8. You already know about approximating them with Riemann sums. They are, after all, limits of Riemann sums. But there's some even slicker approximation methods that we will be treating before too long. So you do have some backup strategies. Head for the WebAssign, practice some odd-numbered problems. You're developing your creativity and persistence skills. And keep on reinforcing, memorize your basic pre-calculus material, such as your laws of exponents and your basic derivative formulas, because those are what give you ideas to solve antiderivative problems. That's all I've got for now. See you soon.